Hey, everybody in Calc BC. Today's assignment asks you to review two more difficult integration techniques that are technically Calc AB material. So I figured I would go over two examples with you just to help you get started. So first one we're going to look at is integration using long division. So when integrating a fraction where the degree of the numerator is greater than or equal to the degree of the denominator, you'll have to use long division to split the fraction. Remember that the degree is the largest exponent. So in this example, the degree is the same, right? We have 2 and 2. So what we're going to have to do here is to split this using long division because this fraction technically represents division. The top is divided by the bottom. And right now, any sort of integration technique that we already know won't really help. So we're going to rewrite this fraction in another form. So we're actually going to perform the long division. So we're going to do x squared minus 4x plus 2 divided by x squared plus 2. And I'm going to include my placeholder 0, which is something you would do for either the numerator or the denominator here. And what's going to happen is, when you do 4 divided by 2 and you get 2, 4 over 2 can now be represented as 2. So we're going to be able to divide this, and whatever we get as a result is another representation of the same thing. So to remind you how to do this, you do the first term, like what multiplied by this first term gives you this first term. And in this case, I could do 1 times x squared to get x squared. So I'm going to write 1 above the ones or the constants spot. And now I take this number and I multiply it by each of these terms and write it underneath. And then I'm going to subtract that whole thing. So we have x squared minus x squared goes away. Negative 4x minus 0x is going to be negative 4x. And 2 minus 2 goes away. Now x squared times something can never give us negative 4x. We ran out of meaningful terms. So really, we get 1 with a remainder. So we write the remainder as whatever was left over the original denominator. So that's now a better way to write this original fraction. So we can rewrite the integral as 1 really minus 4x over x squared plus 2 dx. And that's going to be really nice because the next step is going to be to split this into two integrals. Like that. And obviously, we know that the first integral is going to be x. The second one, now that we've kind of made this into a nicer fraction, we can use u substitution. So I'm going to let u equal x squared plus 2. du is going to be 2x dx. So let's rewrite this. So the first integral just turns into x. The second one, the du needs a 2x, and there's right now a 4x. So we're going to have an extra 2 because it'll be 2 times the 2x. And then this just becomes 1 over u du. And now when I integrate, I get x minus 2 ln absolute value of u. And I need to include my plus c. And now I need to plug back in the x squared plus 2. And if you think about it, technically it doesn't matter. I could plug in any x value in here. This x squared plus 2 is never going to be negative. So I can technically rewrite this without the absolute value bars and still mean the same thing. So that's my final answer. So that is how we do that first example. There are a few practice problems then that I would like you to try, and the answers are available on the last page. And now we're going to try completing the square. This is just another technique that is sometimes useful in integration when you have a situation where u substitution or any other integration method won't work. It is only really useful if the numerator is a constant and the denominator is a quadratic. And the first thing that we have to do is remember how to complete the square. Completing the square is a way to factor a quadratic. So we have to remember that we take this b term, divide it by 2, and then square the result. So I wrote it as b over 2 squared, which in this case, since the b is 4, it's 4 over 2 squared, which is 2 squared, which we know is 4. So what that means is we're going to want to rewrite that denominator so that it's x squared plus 4x plus that new number 4. And the problem is that it was actually plus 8. So we have to think about if we're pulling in a plus 4 inside of our parentheses, what does that mean is left over? And there's 4 more. So it's going to be x squared plus 4x plus 4, and then plus an extra 4. And the reason we wanted to do that is that now we can factor this. Now we have a perfect square trinomial, which can be rewritten as x plus 2, the quantity squared. That plus 4 is still left over outside. And if you think about foiling this, we would end up with x squared plus 4x plus 4, which is what we started with. Okay, so our goal here was to make this into something where the derivative of arctan is present, which is 1 over x squared plus 1. That's our goal. We want this to look like this: 1 over x squared plus 1 dx equals arctan of x plus c. That's always our goal when completing the square. So we're almost there. We could use u substitution right now to get rid of this x plus 2, but we still have a plus 4, and right now there's nothing that can fix that after we apply u substitution. So we're not going to resort to u substitution yet. Instead, we're going to do some fancy algebra. Let's factor out a 4 within the denominator. So we have 4 times, and there's no 4 in the first term. So we're going to introduce a 1/4 so that it would cancel out with the 4, like this, which is a little bit crazy if you haven't done this before. So we have a 4 factored out. To force this to be a plus 1, it kind of messed up the first term. So we'll have to think about that. But now we do have a plus 1, which is what we desperately needed. So that's good. Just to kind of make this a little bit nicer, I'm going to fully factor out the 4 from the integral. So since that 4 was factored out in the denominator, it's going to become 1/4 outside. And don't get confused by the fact that there's more than 1/4 now. But that's what we got. And before we do u substitution, we really want this to turn into something squared plus 1 once we incorporate the u substitution. So what I'm going to do is I'm going to force this 1/4 to become part of this parentheses that's squared. So if I think about 1/2 squared gives us a 4th. So I'm going to transfer it inside of the square to make it x plus 2 over 2. Okay, so think that through. So the 1/4 became a 1/2 inside the parentheses, because when I square it, it'll become 1/4. And now we can go to u substitution. So I'm going to say the u is x plus 2 over 2, which we could rewrite as 1/2 x plus 1 if we distribute the denominator. And the reason that's useful is only because then we know that du is 1/2 dx. We can take the derivative of that much easier than thinking about it as x plus 2 all over 2. Okay, so that's good because now I can change my integral to u form. The x plus 2 over 2 is sitting right here nicely in the denominator. The du is 1/2 dx. I don't have a 1/2 to automatically clump with the dx. So if I want a 1/2 to be over here, I'm going to have to multiply by 2 in front. So we've got 1 over u squared plus 1 du. And so now I have 1/4 times 2, which is just going to be 1/2. The integral of 1 over u squared plus 1 is going to be arc tan of u. And I need my plus c. And I know that my u was x plus 2 all over 2. So I end up with 1/2 arc tan of x plus 2 over 2 plus c. And that's the answer. All right, so both of these techniques are, you know, a little bit more involved than a lot of our A-B integration techniques. So I did want to show you this review. Go ahead and try these. Let me know how it goes, and I wish you the best of luck. Have a great rest of the day.